So we start first time seminar in this semester, and our first speaker is a member of the M Center team, Lino Amorim. So happy to have finally our local people here, and the title is Enumerative Invariants from Categories. Lina, please.
Thank you very much, Jan, for the invitation. Long-time listener, first-time speaker. So, okay, so what I want to talk about today is, so it's this title is based on work with Juno 2 and Shanghai Tech. So let me maybe start with kind of a story first. Of course, this is a M seminar, right? So this story has been told many times, but okay, maybe it bears repeating. So when we look at this the mirror symmetry, so in the early days, so the mirror symmetry is something about Calabi-Yau. In fact, Calabi-Yau threefolds, but more generally Calabi-Yau. So what this mirror symmetry says? So this physicist told us that, okay, so we have a Calabi-Yau X, let's say compact, and then there should be a mirror to that, or maybe more than a mirror, but at least one mirror, X check. And then, so initially, so they will do things like curve counting in X, so which we now call Gromov-Witten invariants of X, at least in genus 0, and this should magically match with some period integrals in the mirror X check, right? So this has something to do integrating this holomorphic volume form in the mirror, and this should kind of magically match, okay? So later on, Kontsevich came in this famous ICM address, and he proposed that actually there should be a fancier version of this mirror symmetry correspondence, where instead of this on the one side, instead of taking this curve counting, you still do some kind of curve counting, but more complicated, and you look at this category, which we call the Fukaya category of X, which is a invariant of the symplectic geometry of X, and that category should be kind of derived equivalent to the category of coherent sheaves in the mirror, or some maybe DG enhancement of that. And so then this mirror symmetry, this philosophy that the symplectic geometry of our space should match in some way the complex geometry of the mirror. And so there are these different levels of, which we maybe call enumerative and homological mirror symmetry. And then, of course, these things were later generalized to not only X is a Calabi-Yau, maybe X is fun or even general type. And in this case, so mirror symmetry becomes slightly less symmetric. And so I have kind of symplectic biases. So won't change anything on the symplectic side on this first column here. So X will be Fano, and then I still take Gromov-Witten invariance in Fukaya category. But now the mirror becomes slightly more complicated. Instead of just a space X check, it must come with a, so it now no longer be compact, it will come with a holomorphic function, or maybe in some other cases not holomorphic, but let's say holomorphic function. And then we have to kind of modify the invariance on the right-hand side. So instead of taking these period integrals, there's this theory of primitive forms by Saito, and that should replace these period integrals. And instead of category of coherent sheaves, we should take the category of matrix factorizations of this function W. Okay, and we should still have this sort of same equivalences. So the idea already in Kontsevich's ICM address was that not only the second line, the homological version of mirror symmetry, is not just like fancier because it involves A-infinity categories and so on, it should be stronger than the enumerative one, in the sense that the enumerative one should follow from the homological version of mirror symmetry. Okay, so that's kind of the proposal, is that the homological mirror symmetry statement should imply the enumerative mirror symmetry one. Okay, so what's the kind of idea here is that, so if we look at all the categories that pop up here in these two little tables, so the Fukaya category of coherent sheaves, matrix factorizations, so these are all examples of what we call Calabi-Yau A-infinity categories. Okay.
Do you allow Z2 grading or just
yes,
Z?
Yes. I allow Z2 grading. Yeah. So in general, so this Fukai category will only be graded when X is has a trivial first Chern class. So in general, it will be just Z2 graded. There are like some intermediate cases, but we usually consider Z2 graded. Yeah. And then all these other invariants that pop up here, so this genus 0 part of Gromov-Witten invariants, these period integrals, these primitive forms, they all can be organized into something called a Frobenius manifold. Okay, so that's how they can be axiomatized. So this Kontsevich proposal, it could be realized if we had a machine that would eat some Calabi-Yau infinity category, maybe with some extra stuff added in, and would spit out a Frobenius manifold. Okay, so this would be the kind of ideal way to realize this homological implies enumerative mirror symmetry slogan. Okay, so of course this this machine shouldn't be like completely random, so it should satisfy some kind of easy property or some kind of fundamental properties. So the first one is kind of more structural, should be just that if two categories of this type are Morita equivalent, so a way of phrasing this is that after you take this triangulated and split closure completion, they become quasi-equivalent. So if we have two Morita equivalent categories, then if you apply this machine to both of them, you should recover isomorphic Frobenius manifolds. Okay, so this would be kind of the first thing. And then the second one would be that if you feed it the correct category, the correct answer comes out. Meaning, so if you feed it the Fukaya category of a symplectic manifold X, one would hope that the output would be the Gromov-Witten invariance, like the geometrically defined Gromov-Witten invariance of X. And similarly for the other categories. So if you feed in this category of coherent sheaves, you expect to get these period integrals in the Calabi-Yau case and so on and so forth. Okay. So of course here in this, if you look at these tables, so in this Gromov-Witten invariance part, right, I'm always writing this genus 0 part because Gromov-Witten invariants have a like obvious generalization from the ones I'm describing here. You can just take curves in higher genus and you get more invariants. And in that case, they cannot be organized into a Frobenius manifold. It's a more complicated algebraic structure, which is usually called a homological field theory, okay? For which there isn't like a very good description of what it is other than it's basically like algebra over this operator given by the cohomology of the Lin-Mumford spaces. So if you wanted to be kind of more ambitious in this project, we could say, okay, so I want a fancier machine that spits out what would be the Gromov-Witten invariance of the category in all genus. And then, of course, we'd like to satisfy basically the same kind of formal properties as the genus 0 one.
If it's smooth and proper, probably.
Yeah. So this is in the extra conditions. So at this point, I'm just.
Yeah, but then this more ambitious goal is more or less a theorem, or I don't know.
Yeah. So I'll describe the status of the two approaches. Okay. So basically the idea is that in genus 0 there is an approach that kind of works, seems to work, and in some cases it actually works. And in this full genus 1 there is like a kind of a proposal that should work, but we don't know other than just a few examples. But let me get into that. So let me start with the genus 0 part and explain what is the setup, because so genus 0 things are much better understood. Okay, so what's these extra conditions that I mentioned? So we'll assume that our infinity category, so like Jan asked, so we only require Z mod 2 graded, but could also be Z graded, but we want smooth, proper, and unital. Okay, so unital is clear. So there's always this question like strict units, cohomological units. It's not a big deal because even if it's just cohomological, we can turn it into a strict unit. So that's not a huge deal. So just unital. Proper means finite dimensional Hom spaces, at least after taking cohomology. And smooth is slightly more technical condition. It has something to do with the diagonal bimodule being perfect. Okay. So we assume these three things from now on from all our categories. Okay. And then these extra conditions are not just conditions, are in fact data. So we need two extra pieces of data, at least can be think about this way. So one is what sometimes called a weak Calabi-Yau structure. Okay. So that can be described as, so it's a bimodule quasi-isomorphism between the diagonal bimodule and the dual one for the category. Okay. So if you want to, instead of thinking categories just on a single A-infinity algebra or even DG algebra, that's fine. So we just want the diagonal bimodule to be isomorphic to the dual one. Okay. And we want to pick a quasi-isomorphism. And so this is what this weak Calabi-Yau structure is. Okay. So actually this can be described slightly differently because this space of Homs between the diagonal bimodule and its dual is actually isomorphic to the dual of Hochschild. And in fact, this is isomorphic to actually Hochschild under our assumptions.
Lina, maybe for the sake of graduate students, you can explain what geometrically does it mean in, I don't know, for Fukaya or for Debye-Koch?
Yeah, so this is kind of like a Poincaré duality or Serre duality, depending if you're more symplectic or real or algebraic person. So yeah, it will kind of guarantee that this Hom spaces satisfy a sort of Poincaré duality or Serre duality. So Hom from A to B will be dual to Hom from B to A. That's kind of the main output of this condition. The other
is the extra piece of data sort of a choice of holomorphic n form, or is it like a section, or is it just the existence?
No, we actually need to choose one. Yeah, okay. For certain things. Yeah, so we actually need a choice, and then we need actually more than that. We need what's called the splitting of the non-commutative Hodge filtration. Okay, so this in general. So there is this spectral sequence that starts with the Hochschild homology and converges to the negative cyclic homology of the category, and we want an actual splitting of this. So an isomorphism between the Hochschild that join this extra variable u and the negative cyclic. So the thing to have in mind here, the parallel is with a complex manifold, right? Where we have a spectral sequence that goes from the Dolbeault homologies to the de Rham homology of the space, right? And this scalar, the fact that we have this famous theorem, right? That if your space is scalar, then this actually degenerates the spectral sequence. And so the de Rham homology is just a direct sum of the Dolbeault homologies. So this is kind of a non-commutative analog of that condition, but we actually want to make a choice. So of course I have to mention here that the existence of these splittings is, according to a conjecture by Kontsevich and Saito, this should always exist under our assumptions that the category is smooth and proper. Okay. So this is actually a theorem in the Z-graded case by Kaledin that such splittings do exist under our assumption that it's smooth and proper. In outside that case, I don't think this is known, but in like complete generality, but it's a conjecture. Okay, so this is the setup. We need these two things, okay? Splitting of the Hodge filtration and this weak Calabi-Yau structure. And then what's the approach? So the approach is due to works of many people. And the approach is as follows. So it goes into two steps. So the idea is that out of this setup, we should produce what is called a variational semi-infinite Hodge structure. And once we have that, we make an extra choice, and out of this we produce a Frobenius manifold. Okay, and that's our like machine to produce Frobenius manifolds out of categories. Okay, so the first step, I don't want to go like into details of what these steps actually do, but I'll just explain kind of the general setup. So the idea is that in the first step, these extra pieces of data their existence is required, but their actual choices is immaterial, okay? So we can produce a variational semi-infinite Hodge structure given that data, but it's independent on the data other than just the category. Okay, so what's the idea here is, okay, so just like in a case of a complex manifold, right, the deformations of a complex manifold are controlled by this cohomology of the tangent sheaf. So for a category, we have the Hochschild cohomology. So infinitesimal deformations of the C are controlled by the Hochschild cohomology. So then what we do is we take basically a kind of power series on this, or maybe do all of this, and let's call this R. And so then what we do is we take, so this is what this versal deformation that pops up here is. So this guy here is basically a R linear A-infinity category that parameterizes basically all possible deformations of the A-infinity category. Okay, so that
do you use? I mean, I see that you use negative cyclic homology rather than periodic cyclic homology. Is there a reason for that?
No, usually, right? I mean, it's kind of in my definition of variation semi-dimensional structure, right? So we want to have something like a RU free module.
Mm-hmm. Oh, okay.
But yeah, there's really no big difference.
Okay, all right.
Yeah. So then what we do, we take this big category, right? This category C, and we take its negative cyclic homology. And this comes with like some extra structure. So one is an analog of the Gauss-Manning connection, or like when you have deformations of a space, which in this infinity setting was worked out by Getzler. So that's why I put that thing there. So you can sometimes call the Getzler-Gauss-Manning connection that exists on this space here. And this thing also comes with a pairing, which is usually called the higher residue pairing, which is kind of a lift of what's often called the Mukai pairing on the Hochschild homology of the category. Okay, and so this structure, so you have a connection, we have a non-degenerate pairing. So the way this goes is that the fact that our category is smooth and proper guarantees that this pairing is non-degenerate.
Sorry, again, for the sake of graduate students, would you like to mention some references, names, or whatever?
Yeah, so this is spread in many places, so I kind of always afraid to forget. So a place where this is, there's a paper by Nick Sheridan. It's called Formally Non-Commutative Hodge Theory, that basically works out all these things, this entire thing. Okay, so that's maybe the most comprehensive place. And then, of course, it has references to kind of the first places where these things popped up. So this Mukai pairing, higher residue pairing that showed up by Shiklarov first. This connection also was originally done by Getzler. There's work by Kontsevich and Solomon on the extension of this connection in the U direction and so on. I think it was the first place that it appeared. But maybe a good, most comprehensive thing which has this statement would be this paper by Nick Sheridan. And okay, so we have this kind of complicated structure, which is, again, independent on the specific choice of this extra data, okay? Depends only on the category. And then the second step is, so out of this data here, we want to produce a Frobenius manifold, okay? So remember, Frobenius manifold, we have to have a flat metric and a product structure in the tangent bundle to our space. Actually, we want just a formal Frobenius manifold. So, and with this flat metric, and then the metric together with the product turns every tangent space into a Frobenius algebra. Okay, so to actually produce the second arrow, okay, so this is basically complete analogy to what happens in Saito's work in this unfolding of singularities, so what we call a primitive form. So we call this a categorical primitive form. So we basically have to choose kind of a special element in this variational semi-dimensional Hodge structure, which has like a kind of long list of properties that, in my opinion, are not very enlightening. The most important thing is that we wanted such that if you take a derivation, so an element here, so derivative in the R direction, and you apply this connection, in the v direction to this primitive form, this map defines isomorphism between derivations of R and the Hochschild homology of the category. This idea is that this should be an isomorphism. This is kind of the most fundamental property of the primitive form. Then here's like many other properties, kind of a list involving some compatibilities with the Gauss-Manin connection and the higher residue pairing. Okay. And the important thing here is that this guy here, so the omega 0 and S, do determine a primitive form. Okay. But to actually get the primitive form, we did some extra properties on the splitting. Okay. So the splitting, remember, was just this sort of isomorphism. But to actually get a primitive form, we want these things to respect the pairings that exist on both sides and some special property with the connection on the U direction. Okay. But so if you have those, then you can produce a primitive form. And then out of a primitive form, there is like a construction that provides a Frobenius manifold. Okay. So that's kind of basically the general setup. Okay. So the kind of what I want to highlight here is that, so we do get a way to produce a Frobenius manifold, but the kind of the main point here is that this is not an invariant just of the category, it's an invariant of the category and these two extra pieces of data here. Okay, so the situation is kind of more complicated than we had before, right? So remember, one of the main goals that we have for this construction was that, okay, if you feed it the Fukaya category, you want to spit out the Gromov-Witten invariance of X. But now, according to our setup, the input is not just an A-infinity category. We need these extra pieces of data. So then the question is, okay, so what is the correct input here to the machine to actually produce the Gromov-Witten invariance of X? Okay, so I wanted to maybe just spend a slide on that. So what happens for the Fukaya category? Okay, so the point is that we need to choose the correct Calabi-Yau structure and the correct splitting in order to produce the Gromov-Witten invariance of X. Otherwise, you get something that is less geometric. So to do that, so there is at least conjecturally a way to choose that. So this is this thing called the open-closed map. Okay, so part of this gadget of study of pseudo-holomorphic maps that shows up in symplectic geometry that produces Gromov-Witten invariants, Fukaya categories, and so on. There's also some kind of intermediate data that provides what is sometimes called the open-closed map. So that's a map from the Hochschild homology of the Fukaya category to the cohomology of the underlying space, maybe with some coefficients in some Novikov ring, okay, and some shift depending on the dimension of the symplectic manifold, okay. And the point is that it's expected that for maybe a wide class of symplectic manifolds, this map here is expected to be an isomorphism, okay. So we don't know exactly what's the correct range for this statement, but for most examples that we know about, this should be an isomorphism, okay. And then there's like a fancier version of this open-closed map that we might call the cyclic open-closed map, okay, which is kind of very similar, but instead of having inputs Hochschild, you replace it by negative cyclic, and then the output is, it's basically the same thing, we just adjoin this formal variable, okay. And so the idea is that, oh, if the open-closed map is an isomorphism, the cyclic version should also be an isomorphism. And then we can do as follows. So we pick our splitting to be the unique splitting that makes this diagram commute here. Okay, so where this map, the lower map here, lower horizontal map, is just inclusion, okay? So you take a vector space and you include it on the same thing, a joint U, just on like U equals 0 component, okay? And then if these both vertical arrows are isomorphisms, that determines a unique map there, which will be our splitting, okay? And the claim is that this is the correct splitting one should consider, okay? Similarly, we can produce a Calabi-Yau structure just by composing just an integration map, if you want, right, on cohomology of the underlying space with the open-close map. And now with this composition, this will define a weak Calabi-Yau structure. Okay, again, under the assumption that this open-close map is an isomorphism. Okay, and then the conjecture is that for these two choices, if we apply this, our machine, to this triple of the Foucault category, together with Calabi-Yau structure and the splitting chosen using the open-closed map, the output of this construction is a Frobenius manifold, which is isomorphic to the Frobenius manifold that we get by considering the geometrically defined Gromov-Witten invariants. Okay, so that's at least the conjecture. And we know, in fact, this is true in some cases. So kind of mention my own work here with the Juno tool, where we prove that this conjecture is true when the Hochschild cohomology of X is a semi-simple ring. Okay. So I want to just point out a couple of things about this work. Okay. So this work actually does not use this cyclic open-close map. Okay. So in this, under the simplifying assumption that the semi-simple ring, the Hochschild cohomology is a semi-simple ring, the space of splittings for this guy is much simpler than in general. And the point is that just the open-close map is unique to pinpoint a splitting. Okay, but it should agree with this splitting here that shows up in this diagram. But we actually don't need the existence of this cyclic open-close map. Okay, and we get a splitting, and for that splitting, we show that the output of this construction and the actual Gromov-Witten invariants agree. Okay, so this is for people that are familiar with this Telemann's result about how to reconstruct like higher genus in even this classification of semi-simple homological field theories that basically follows from that result. Okay, that you only need to
for what X it's semi-simple. Can you give examples?
Oh yeah. So if we take X to be a toric Fano manifold with a generic symplectic toric symplectic form, this will be semi-simple. So in the toric case, in the Fano toric case, right, this is equivalent to the statement that this Hori-Vafa, the mirror potential, is a Morse function.
And this Hochschild cohomology, that's essentially quantum cohomology of X.
Yes. Yeah, in these cases, we know that the Hochschild cohomology is isomorphic to quantum cohomology. So this is equivalent to the quantum cohomology being semi-simple. Yeah, so in this case, for example, the easiest case would be CPN. CPN would fall into this statement. And yeah, so this is so basically this is the picture in genus 0, okay? And so the idea why this works in genus 0 is because we have this description of what Gromov-Witten invariant should be in terms of this structure that is called the Frobenius manifold. Right? So the problem in higher genus is that there is no analogous description like that. We don't really know how to axiomatize Gromov-Witten invariants in all genus other than just is something with an action from the cohomologies of these the Lin-Mumford spaces. So we have to build in these curves acting on our theory. So what's the approach in higher genus? Okay, so the approach in higher genus, so the one, at least the one I'm kind of familiar with, is this what's called the categorical enumerative invariance. And so this is based on kind of relatively old work of Costello and more recent work of Costello, Colorado and Tu, where they kind of more or less reformulated Costello's older work, okay, which is also based on work by Kontsevich and so on. Okay, so what's the setup here? So the setup here is slightly different. So here we start with a unital, A-infinity category or algebra, if you prefer. Maybe algebra is easier to think about. But now we require it to be cyclic. Okay, so what does this cyclic mean? So I'll just pretend from now on that our category is an algebra, just a single object for simplicity. That just means that we have an inner product, okay? And the inner product is compatible with the infinity operations in the sense that this equation here, so this thing where we take the mn operation and then we bracket with the n+1 element, this operation is invariant under cyclic permutations of the inputs up to some causal sign. Okay, so that's what cyclic means. And so the input now is we want one of those. So an infinity category is cyclic and unital, and as before, a splitting of the Hodge filtration. Okay, so again, not arbitrary. We wanted to have some compatibility with this Mukai pairing and higher residue pairing. So that's sometimes called symplectic. Okay, so we want one of those splittings. And so then what's the output of this construction? So the output is this sequence of maps. So for each genus and number of inputs, so you get a map which takes input n elements on Hochschild of the category adjoint U here. Okay, so these powers of U, if you're familiar with Gromov-Witten invariants, is the same as this descendant Gromov-Witten invariants, where we input powers of the psi classes in our moduli spaces. That's the U takes the role of keeping track of those. So the idea is that we should put all of this together. We get this big potential that we should think on as the descendant Gromov-Witten potential of the category. Okay, that's the output. So we don't get exactly a cohomological field theory. We get just the descendant Gromov-Witten potential of what should be like the full cohomological field theory, but we don't get an actual cohomological field theory. Okay, we just get this bunch of numbers that look very much like Gromov-Witten invariants of a space, but we actually don't know how to prove most of the axioms that the Gromov-Witten invariants do satisfy. At least at this point, we don't yet know how to do that. We know maybe some of them, but not all. Okay, so what are the main ingredients? For the construction is kind of slightly involved, so I don't want to go into like full details, but I just want to mention what are like the main ingredients on the construction. So the way I see it, there are basically two main ingredients. So the first one is this, and this is basically due to Kontsevich and Soilman, is the following. So we'll denote by this MGKL frame to be the modular space of smooth Riemann surfaces of genus G with K plus L marked points, and they are split into K inputs and L outputs. And this frame here means that we have parameterizations of small neighborhoods of each of the marked points. Okay, so again, this is just smooth Riemann surfaces. So we don't consider nodal curves or anything like that, like we do in Gromov-Witten theory, for example. So then we can take chains on this space, and then chains on this space acts on the Hochschild complex of our category C. Okay, so for each K and L, we have in a chain in here, we get a map with K inputs and L outputs. And this map is compatible with sewing of Riemann surfaces. Okay, so since our Riemann surfaces are framed near the marked points, we know how to glue them, okay, using these parameterizations. So these maps here are compatible with sewing of these Riemann surfaces, okay? So the main idea that makes this work is that we have a combinatorial model for these chains here, given by some version of ribbon graphs, okay? So we have these things. So this is the first ingredient. So again, this is due to work of Kontsevich and Soilman. The second ingredient is the following. So if we take all these moduli spaces and we consider chains on this, but we take this kind of homotopy quotient, okay? So we have a lot of things acting here. So we have the symmetric groups acting on the marked points just by relabeling them. And we have S1 actions on each of the marked points. So what's the idea here? So if you have your surface, for around each marked point, we have a parameterization of that neighborhood. So there's a S1 action here, which is just rotating in the unit circle on C. Okay, so that gives us an S1 action at each marked point. Okay, so we take a quotient by that, all those S1s and all the symmetric groups acting. Okay, so if we do that and then we put all these guys together, oops, if we put all these guys together, we get this huge vector space, which turns out to be a differential graded Lie algebra structure. Okay. So whenever you have a differential graded Lie algebra, we can write down this Morang-Cartan equation. And what Costello proved, and so this is based on this work of Zibach in physics, is that this DGLA has essentially a unique solution to the Morang-Cartan equation. Okay, and so these are in the physics literature called string vertices. Okay, so what does it mean by unique? It's not actually unique, but it's unique if you fix the M03 case. Okay, so genus 03 mark points. So if you fix the value of the Morang-Cartan element there, then it's unique up to gauge equivalence. Okay, so that's the statement. And these are kind of the main two ingredients of this construction. So then how does the construction really go? So let me just briefly explain here. So we have this huge Lie algebra, G hat, that was explained above. And then one can construct a very similar, at least formally similar, DGLA on the Hochschild, or using the Hochschild complex of the category. Okay, so you basically do a similar construction. You take some Hom spaces. In this case, there's like some continuity. I'm being slightly vague here, but the idea is you take the negative cyclic complex of C, and then you take the kth symmetric power, and then L symmetric power on the output, but now we take the positive cyclic. So it's a slightly weird construction why it takes sometimes negative, sometimes positive, but that's kind of more technical thing. But it's basically we do something which looks formally very much like what we had before. And this row here, this action, turns into a Lie algebra map or a DGLA map between these two Lie algebras. Okay, so now this is a DGLA, this is a DGLA, and this is a map of DGLAs. Okay, and in here, we have this unique Morang-Cartan element, so we can push it forward here, basically. And here we'll get a new Morang-Cartan element. And so then the idea is that, so this algebra is kind of terribly complicated, this DGLA, but actually we can consider a much simpler one, which is isomorphic to it, which is we take the symmetric algebra just on positive cyclic homology of C, okay? And so this is a isomorphism of the DGLAs, but actually this guy here has trivial Lie bracket. That's kind of the main upshot. And this isomorphism here depends on the splitting of our non-commutative Hall filtration. That's kind of the main idea here, is that this first part here is kind of categorical, but this second map here, this kind of trivialization, is depends on the splitting. Okay, but then the idea is now this guy here should have a corresponding Morang-Cartan element here. Okay, but here, because the Lie bracket is trivial, a solution to the Morang-Cartan equation is just a closed element. Okay, and so then you just write down what it is, and we get this. We can decompose it into this some kind of these FGNs that I mentioned in the beginning. Okay, so this is kind of the basic story of the construction. Okay, is this action here gives a way to push forward these string vertices to this categorical version, and then one trivializes the circle actions, and we get what should be our Gromov-Witten potential. Okay. So of course, I'm kind of skipping many details here, but this is kind of the general field of the construction. Okay. So what's the upshot here, right? So what do we want to do? So we want to do what we had for the genus 0 case. So the first item in our shopping cart, right, shopping list was we want to have a construction which is Morita invariant, okay? Meaning if you take two Morita equivalent categories, you should produce the same answer, okay, or isomorphic in some sense, okay? So the first thing we want to do is want to prove Morita invariance of these categorical enumerative invariants. So there is like actually several problems. So the first one is that even the way this is set up is this, we start with a cyclic A-infinity category, and being cyclic is not preserved, not even by A-infinity isomorphisms, much less Morita equivalence, okay? So we need to fix that. And the second problem is that even if this was preserved by cyclic A-infinity isomorphisms, these maps row here, which kind of make this construction work, are not functorial in any way. So that's kind of the two main obstacles to make this work. So what's the solution? So the solution is to think in terms of non-commutative symplectic geometry. And once again, this kind of ideas and much of the execution actually come from Kontsevich and Soilman's paper on like notes on A-infinity categories. Okay, so what's the idea here, right? So the idea here is we want to think on this cyclic pairing on our A-infinity, let's say algebra for simplicity. So we can think on it as giving us an, oops, something went wrong here. So we want to think on this as a element on the dual to the positive cyclic Hochschild. Okay, so we can think about that. And so this is a theorem proved by Kontsevich and Soilman that this is actually isomorphic to what in non-commutative geometry terms, right, would be the space of closed two forms in our category, okay? So if you want to think in slightly more algebraic and not geometric terms, so this is a special type of homomorphism from the diagonal bimodule to the dual, which is antisymmetric and it's closed. The antisymmetry is easy to understand what it is. The closeness condition is harder. It really is being closed in the, from the point of view of the Ram differential, but purely algebraically is a kind of stranger condition to look at, okay? But then the point of view of this non-commutative symplectic geometry is that we should think on these cyclic pairings as being just closed to forms which are in a very special form. So they are basically written in the coordinates we choose, they are constant, okay? So the idea is that we should think on cyclic pairings as constant symplectic forms, and the thing we are looking for are just arbitrary symplectic forms. So if we want to go from arbitrary symplectic form, right, to a constant one, in symplectic geometry, we have the Darboux theorem, right? So what we want to have some sort of Darboux theorem to start from an arbitrary symplectic form or non-commutative symplectic form and turn it into a constant one. Okay, so that's kind of where we're headed. And in fact, this is not exactly what we need. We need unital versions of that. Okay, so what's the kind of upshot here, right? So we want to have the same setup that we had in genus 0, right? So in genus 0, we started with one of these smooth proper unital categories, and then this weak Calabi-Yau structure and the splitting. Okay, so it turns out that if you apply the splitting to the weak Calabi-Yau structure, this is what's called a strong Calabi-Yau structure, and that's equivalent to one of these non-commutative symplectic forms. Okay, so this produces a symplectic form. Okay, so then what we would like to do is to, okay, now apply Darboux theorem and go from a symplectic form to a constant symplectic form. So in other words, a cyclic A-infinity category, okay? And then we want that, so the idea, we want the output, right? So the cyclic infinity algebra or category that we get shouldn't depend on all these choices that we made. So we want some kind of Moser stability theorem also, right? That guarantees that two symplectic forms are in fact symplectomorphic, okay? And so, and this is the place where it differs from classical symplectic geometry, is because we want everything to be unital, basically. Okay? So we want to have unital versions of all these constructions, okay? Which is surprisingly, there's some new phenomenon going on, okay? And because of that, we have a slightly strange setup, which I'm not like 100% satisfied with that, but it's what we have at this point, right? So the setup is that we don't want just to start with an arbitrary Calabi-Yau structure and a splitting. We want this pair to be unital. So what does it mean? And this is kind of the cumbersome part of the construction. We want that there should exist a split generating subcategory A of this split closed triangulated completion of C, such that for any object in this category A, if you do the pairing between the unit or the identity of that object and this our strong Calabi-Yau structure or symplectic form, this pairing, which should be a function in U, remember, is actually just constant. Okay? So ideally, right, we would like this A to be C itself, but in general, we have to have a Morita invariant notion. We need to work with this A here. But this is kind of the way it goes. And so then what happens? If we have one of these unital ones, there should be a 0 there. If one of these unital ones, we can produce element in the dual of the unital version of positive cyclic. Okay, so unlike Hochschild, for which there is like a reduced version of Hochschild for unital case, which is actually isomorphic to the original one, for positive cyclic, this is different. The positive cyclic homology and this unital version or reduced version of the cyclic homology are actually not isomorphic in general. Okay, but we produce a unital version of that, and that's isomorphic to the what should be the unital version of closed two forms. Okay, and so then now the idea is we apply unital Darboux theorem and unital Moser stability theorem. Okay, so the unital Darboux theorem actually works with no changes to the usual one, right? So in this setting, it says that if we start with one of these unital pairs of weak Calabi-Yau structure and splitting, then you can find a cyclic A-infinity category A prime and an A-infinity isomorphism to the thing we started with, such that if you pull back under this isomorphism, this symplectic form, we get back the constant symplectic form. Okay, so this is exactly the statement of the standard Darboux theorem. Right? So the Moser stability theorem is to guarantee some sort of uniqueness of this construction. Right? So what do we want to say? So I'd like to say that if we have two of these cyclic models, so the output of the theorem above, for the same thing, for the same A, we'd like to say that these two ones are isomorphic, cyclically isomorphic to each other. Okay, and it turns out this is not true in general. Okay, they are either cyclically isomorphic but not unital, or unital isomorphic but not cyclic. Okay, so there's a weird thing going on here, but this is true if the thing we start is even. Okay, so if the Calabi-Yau structure that you start is actually even, of even degree, then the Moser stability theorem works. Okay, the Moser stability theorem only fails in this unital setting if omega 0 is odd. Okay, so this is the only small place where we have a problem. So, and we'll find a way around it. Okay, and now this is kind of our main theorem, is that now once we have this, right, so now what we have to worry about is how do those categorical enumerative invariants change if you have a cyclic isomorphism between two A-infinity algebras. Okay, and so this is the theorem. So if you have a unital cyclic infinity isomorphism from C to D, and if you have a splitting for C, we can push forward the splitting using the infinity isomorphism, and that will produce a splitting on D. So that's there. And then, so F induces a map between Hochschild homologies. And so then the categorical enumerative invariants agree. Okay, that's kind of the theorem. So let me just explain one idea of the proof. Because remember I said that these rows, these actions of the moduli spaces of Riemann surfaces on these Hochschild complexes, this is not functorial. So what we do instead is we take this A-infinity isomorphism and we turn it into what Fukaya calls a cyclic pseudo-isotopy. So that basically what is, roughly speaking, is it's a family of A-infinity algebras interpolating between the original one and the target. That's kind of roughly the idea. And then we go through this entire construction of this map row in families, and we produce a kind of family of actions, and then that's how we prove this theorem. That's kind of the main idea. Okay, so now once we have the theorem, now we are kind of good to go, okay? Meaning we can define something, right? So now again, what's the input? We start with our unital infinity category as before, smooth property and so on, with this choice of a weak Calabi-Yau structure and splitting. And then we apply the Darboux theorem, we produce a cyclic model for it, and then we define the categorical enumerative invariants of our triple as the categorical enumerative invariants of the cyclic model together with this splitting. So the reason we can be kind of not so careful with like where the splitting lives is because we have many functors going on here, right? So we go from A prime to A to the completion of C to C. And all these maps induce isomorphism of negative cyclic homologies, and all of that. So we can transfer splittings from one to the other without any issues. So when I write here S in A prime, it means the splitting induced on A prime following this sequence of isomorphism in all the Hochschild theories. Okay, so this is how we define it. Of course, now we have to worry if this is well defined or not. And the theorem is that this is in fact, independent of all the choices. So meaning the choice of this splitting subcategory, where the splitting is unital, and the choice of the cyclic model, okay? So how does this work? So this should follow exactly from this Moser stability. The problem is that Moser stability doesn't always work, okay? In the odd case, it fails. So in the even case, the theorem just follows from Moser stability and this theorem, right? If we have two different cyclic models, we have a cyclic isomorphism between them, and our theorem guarantees the categorical enumerative invariants don't change, okay? In the odd case, we have a problem, and so our trick to solve this is to reduce everything to the even case, okay? So if we have an odd category, or Calabi-Yau category, what we do is we tensor it with a one-dimensional Clifford algebra, okay? So this is this CL here that I mentioned. So this is basically just an algebra as a vector space is just two-dimensional. It has a unit and a generator in odd degree, and has a single M2 operation. And this is a cyclic infinity algebra, okay, which is almost indistinguishable from just the ground field, okay? But it's odd. So once you tensor with this, you go from an odd infinity category to an even one. And then kind of our theorem is that actually tensoring with this Clifford algebra does not change the categorical enumerative invariants. So we can reduce the odd case to the even case by doing this trick of tensoring with this Clifford algebra. Okay, so I'll say something more in a minute about it. And so once we prove that this construction is independent of all choices, then we can prove our desired Morita invariance result. That if two categories are Morita equivalent, then the categorical enumerative invariants agree. Okay, I mean, under this isomorphism identifying their Hochschilds. Okay, so that's the kind of a main theorem. So but remember, this is just the first step in our shopping list, but it does allow us to compute something. So let me show an example of this, okay, where we can compute this. So start with just a power series, W, which has a isolated, non-degenerate singular point at the origin. Okay, so it's basically think on like x squared. Okay, so in that case, we can consider the category of matrix factorizations of such a thing. So this is known to be smooth and proper and unital. So it turns out that the Hochschild homology is just one-dimensional. And so it's generated by a weak Calabi-Yau structure. And so what's the third thing we need, right? We need is splitting, right? To get something for which we can compute categorical enumerative invariants. And so it turns out that in this case, there is a unique homogeneous splitting, okay? So there are many splittings, but if you impose a condition on this, the connection on the u direction, which is called homogeneity, there's a unique one, okay? So we take that one. And now we can compute Gromov-Witten, or this categorical enumerative invariance for this category with this choice of weak Calabi-Yau structure and splitting. So then what should be the inputs, remember, is for each genus and each n, right? So each input should be a Hochschild homology class together with the power of u. So that's what I have here. These are just copies of phi because it's one-dimensional. And the output here is basically the Gromov-Witten invariance of a point. That's the idea. So what's that? So on MGN bar, right, we have these psi classes. Okay, and these categorical enumerative invariants agree just with the invariance that we get just by integrating the corresponding psi classes on MGN bar. Okay, so what this theorem basically says is that the categorical enumerative invariants of this category agree with the Gromov-Witten invariance of a point. That's the result. Okay, so it's maybe a good place to stop. And questions.
Yeah, thank you very much. So are there any questions?
So this category, this final example of the matrix factorizations.
Yeah.
So this is like a Clifford algebra too, right? Isn't there's a generator or something which is just
yeah. So the way this theorem works, right, is we use this Morita invariance, right, to reduce everything to just this generator, right? And this generator is a Clifford algebra, and these Clifford algebras are all either Morita equivalent to the one-dimensional, right, Clifford algebra, or just to the ground field. And then the categorical enumerative invariants for this Clifford algebra agree with the categorical enumerative invariants of a field. So this basically is that we use our theorem to reduce everything to a field. Okay? And then you have to consider what are the categorical enumerative invariants of just the ground field. Okay? And this was computed, actually the separate work just by Juno too. So my collaborator, he had computed just for the ground field. And this Morita invariance allows us basically to reduce everything to either the Clifford algebra, one-dimensional Clifford algebra, or the ground field. And then you can actually reduce the Clifford algebra to the ground field, and then you just have to worry about the ground field. And then the proof of what happens in the case of ground field is slightly different. Okay, it's basically, it boils down to like describing the compactified MGNs as the string vertices themselves union some kind of bundles over lower dimensional string vertices, and then checking that actually this is exactly how you define this categorical enumerative invariance. So it's actually kind of interesting proof.
And are there any other examples that you look at? Like, I mean, even just with this, just keeping with this matrix factors, could you do just a AN singularity or A2?
That's what we're trying to do.
Okay.
So
Actually, I have a similar question. So if you have something non-Morse.
Yeah, so we have a strategy, okay? We don't know how to do it, but we have a strategy. So the idea is, so our idea is that we should be able to deform to Morse, right? So we start with, let's say, x cubed, and then we deform to Morse, which is basically, so there's actually work by Panaripande and Pixton and someone else, where they essentially do that to understand this Witten's like spin, R-spin homological field theory. And I think we can follow the same strategy here by deforming to Morse. The thing that's missing is, in fact, can be understood here, right? Even in this Morse case, right? I'm saying take this, the unique homogeneous splitting. But the point is, I could take a different splitting, and that should still give you some invariance that should be not the Gromov-Witten invariance of a point. Okay, so the idea is that if you have two different splittings, they should differ by an R matrix. And there's an action of R matrices on the space of homological field theories. And so this is already in the work of like Giventhal and stuff like that. So we want to have compatibility between the R action on the space of splittings and the action, or sorry, the action by R matrices on the space of splittings and the action of R matrices in the space of homological field theories. That part is actually okay. We do know that. There is one other action that we need to understand, and that's kind of where we're stuck now, which is there's this action called the translation action. On at least Panaripane calls it the translation action, which is when you act by an R matrix, if you start with a unital homological field theory, the output will in general no longer be unital homological field theory. And there's like a translation action to fix that. And what we believe is that that action on the space of homological field theories should correspond on our side to changing the Calabi-Yau structure. Right? So even if we fix the weak Calabi-Yau structure, different splittings give you different strong Calabi-Yau structures. And different lifts of this will lead to different cyclic models and so on. So we agree that this, or we believe that this translation action should correspond to this changing the Calabi-Yau structure on the category. And if we can, in fact, check that, and we have compatibilities between this changing of splittings on both sides, then we should be able to prove this by this deformation to Morse idea. But the main obstacle, at least as far as we understand it at this point, is this to have compatibility between these different actions on the space of splitting on our data, which is Calabi-Yau structure plus splitting, and on the space of homological field theories, and check that this construction is compatible with these actions. And then we should be able to do, or even these examples I mentioned before, right? In the toric case, right? We have this CPN, for example. In that case, this is Morse, right? But the point is that we only know how to compute the categorical enumerative invariance for like the dumb splitting, okay? So the like in the semi-simple case, there is a canonical splitting, okay? And we know how to, but which leads to kind of not interesting Gromov-Witten invariance. So we know how to compute the categorical enumerative invariance for this specific splitting. But the one I mentioned above, right, using this open-close map, is a much more complicated splitting. So what we need to do is to be able to compare the categorical enumerative invariance under different splittings on the same category. And see if we have this compatibility between these actions, then we can, for example, show that the categorical enumerative invariance of the Fukaya category of CPN for this correct splitting agree with all Gromov-Witten invariants on CPN. And then via this, the generation argument, we should also be able or morphification argument actually, should also be able to do the same thing for this xn, for example, and show that that should match this Witten's R-spin homological field theory. That's the conjecture.
And this Morse property, how it shows up categorically? I mean, in what place it's the most essential?
So in the previous approach through these categorical primitive forms, what the semi-simple condition does is that it shows that this so what's the this is in Kontsevich's paper. I remember now the exact terminology, but so it's saying that this U connection that you have on negative cyclic thing, it splits into some blocks, and on each block is actually holomorphic. So there's no pole on U equals 0. So originally there's a pole of order 2, but then you should be able to decompose it into pieces, and then in each piece there's just a multiple of identity in power 1 over U squared. Mm-hmm. And then there should be something 1 over U. But in the semi-simple case, there's nothing in 1 over U. It's really holomorphic. And that simplifies a lot the space of primitive form, the space of splittings, and so on.
Basically, it's absence of the monodromy or something like that.
Yeah, it's basic something like that. Yeah. You can decompose this connection into holomorphic pieces, basically. Yeah. So not even just regular, really holomorphic. That's in this genus 0 approach. In this categorical enumerative invariant side it's more computational in a way. It's like the easy splitting, the kind of the canonical one is very easy to handle with. Like there's like, when you compute this many Mukai pairings and so on with like higher terms, all these higher residue pairings turn into just constant things. So it's kind of harder to explain exactly how it helps, but it's just that this semi-simple splitting, it's very easy to deal with. Because like all the higher powers in U involve things that are like in the kernel of the Mukai pairing. So everything simplifies a lot.
Mm-hmm.
Yeah.
Okay, so more questions? Okay, if there are no questions, so thank you very much, Lino, for very interesting talk. And those who did not believe in the cyclic homology, maybe it's time to start to learn what is it, because you can write down some explicit formulas in the end. Okay, anyway, thank you very much, and this is it for today.